Hello everyone. Today we're going to look at our last technique for differentiation, and this is called logarithmic differentiation. It's no longer in the AP curriculum. I found out that it was omitted many years ago without me knowing this. I teach it anyway, so let's review. If you recall, in class, we proved that the derivative of the natural log of x is equal to 1 over x as long as x is positive. All right, now we would like to extend this to all numbers not equal to 0. Notice the domain for the natural log is all positive values of x. So what we'll do is we'll define the square root of x squared as the absolute value of x. So we know that we are taking the natural log of a positive number. So let's find out what we get when we use the chain rule on this by rewriting it as the natural log of x squared to the 1/2. So the derivative would be, now let's just recall that if we have the derivative of the natural log of a function of x via the chain rule, because the natural log is the outer function and the function of x is the inner, by the chain rule, we differentiate the outer at the inner. So the derivative of the natural log is 1 over something, which is f of x, if we think of this as a u, times the derivative of the inner. So here, if we take a look at this, we could consider this as the inner function and this as the outer. So the derivative of the natural log of anything is 1 over whatever the inner function is times the derivative of the inner. Now, even though I would never differentiate this way, I would multiply 2 times 1/2. Let's not do this here. So we use a chain rule on that piece. So here, the outer function is the exponent and the inner function is x squared. So we could rewrite it as the derivative of the outer, which is 1/2 x squared to the negative 1/2, times the derivative of the inner, which is 2x. Now let's simplify that and see what we get. So we notice that the 2's would cancel, the 2 and the 1/2, I believe. So let's just cancel those out. Okay, so 1/2 times 2 is 1, and the x goes in the numerator. So we would end up with x over the square root of x squared, and then this piece would go in the denominator, which is another square root of x squared, which can be rewritten as the square root of x to the 4th. Now, because x to the 4th is always positive, the square root will always be positive, and we could write this as x over x squared, which simplifies to 1 over x. So we can now conclude that the derivative of the natural log of the absolute value of x is just 1 over x, but now we extend the domain for all x not equal to 0. And that derivative we'll need later when we get to integration, right? This derivative we'll need later when we get to integration. But right now we're focusing in on this one. Okay. Now, I'd like to show you a technique that uses the natural log to differentiate. And this is called logarithmic differentiation. And it's very important to remember the derivative of the natural log. Please note that here we'll assume that x is positive always. And whatever we're taking the natural log, we'll assume that that quantity is positive. And also please note that when we take the derivative, with respect to x of the natural log of y, we could think of y as f of x. By the chain rule, this would be 1 over y dy dx, which is also implicit differentiation. Okay, so let's keep that in mind for the lesson. Okay, so let's take a look at number 2. Now, if we were asked to find the derivative for number 2, then if we do this by brute force, that's the function, excuse me. Let me just erase that. So if we do this by brute force, we would have to use the quotient rule, the product rule, and the chain rule. And notice that the quotient and product rules are fine. We have exponents, an expression to a power, which would force us to use the chain rule. And that's fine. We can, of course, do that. But when the expression has division and multiplication, we know that these rules apply. The natural log of a product is the sum of the natural logs. The natural log of a quotient is the difference of the natural logs. And the natural log of an expression to a power, a numerical power, is k times the natural log of the expression. So these rules for natural logs apply. And what's beautiful about the natural log of a quotient or a product or an expression to a power is that we could convert it into an addition problem or subtraction problem or a scalar multiple. So we would like to take advantage of that. And in mathematics, division and multiplication are more difficult operations than addition or subtraction. So if we could change multiplication and division into addition and subtraction some way, then it would be so much easier to differentiate. So this is what we do. We take the natural log of each side, assuming that each side is positive. Technically, we should take the absolute value of each side and then take the natural log, but I will skip that step. And the reason why we could take the natural log on each side is that we've discussed that the natural log is a one-to-one function. So I really should write it this way. We're assuming y is positive and the right side is positive. So we'll have the natural log of y and the natural log of the right side. And we have this. Now, we're not ready to differentiate this. We're going to prep it for differentiation. We're going to use the rules of logs first to rewrite the numerator as a sum, because we have the natural log of a product, and the denominator as a difference. Okay, and then of course, we could bring those exponents in the front of the natural log. And now we differentiate both sides with respect to x, just like we do for implicit differentiation. Okay, so the derivative of the natural log of y, as we said before, is 1 over y implicit differentiation. And here on the right side, we're taking the derivative of the sum or difference, and we have inner functions here, so we're going to use the derivative of the natural log of a function. So we bring down the scalars, we don't need a product rule, and we differentiate. So the derivative of the natural log of x is 1 over x. The derivative of the natural log of 1 over 5x plus 1 is 1 over 5x plus 1 times 5, because that's the derivative of the inner function. And the derivative of the natural log of 3x minus 2 is 1 over 3x minus 2 times 3. Now we're going to solve for dy dx. And to solve for dy dx, we multiply each side by y. And we have 2 over x plus 5 over 2 times 5x plus 1 minus 9 over 3x minus 2. And again, finally, the last step is to substitute back what y is, which is x squared times 5x plus 1 to the 1/2 over 3x minus 2 cubed times, and we just bring it down. And this would be the derivative of our complicated expression. Notice that with logarithmic differentiation, we always get the expression back in its derivative, which is quite interesting. We'll always have to bring over a y when we differentiate the natural log of y with respect to x. And if we had used the quotient, product, and chain rule here, we would have gotten an answer that's equivalent to the one that we obtained here. So let's just summarize. So when we use log differentiation, we don't use it with everything. We use it when the function has a multiplication, division, and powers. So if the function y equals f of x consists of products, quotients, and powers, take the natural logarithm of each side. And again, this is because the natural log function is 1 to 1. Then simplify using the properties of logarithms. So division becomes subtraction, multiplication becomes addition, and powers become scalars or coefficients to the natural log. Then we differentiate each side implicitly with respect to x using the fact that the derivative with respect to x of the natural log of y is equal to 1 over y dy dx. This will appear in every natural log differentiation problem. And we always bring the y over, solve for dy dx, and replace y, which will appear on the other side with f of x. Okay, so let's try it now. And what's nice is that when we're really stuck, we could use log differentiation to find the derivative. So let's take a look at something like y equals x to the x. Now, we've never considered how to differentiate a function to a function. We know how to differentiate x to a number, right? The derivative of x to the fifth is 5x to the fourth. We will talk about how to differentiate e to the x, which is just e to the x. We'll talk about how to differentiate any exponential function 2 to the x. But what happens when both the base and the power are variables? Well, that's when we really need logarithmic differentiation. There is no derivative rule to memorize. We have to use log differentiation. So let's try it. So we'll take the natural log of each side. And here we can move the x in front of the natural log of x using the exponent rule for logarithms. We differentiate each side with respect to x. This piece you can skip, but I'm writing it out now just for emphasis. So we get 1 over y dy dx on this side equals, now on the right side, we must use the product rule because we are multiplying two functions of x's, right? The x is a function and the natural log of x is a function. Okay, so we have the first times the derivative of the second plus the second times the derivative of the first. We bring the y over. And our final answer is x to the x, when we replace the y back, times 1 plus the natural log of x. And this is the derivative that we seek. This is the derivative that we seek. Okay, so pause the video and try this next problem. Find the derivative if y equals sine x to the tan x, and use the previous problem as a guide. Okay, so try it and we'll check our answers at the end. So I've written out the solution. First, we take the natural log of each side. That's this step. And we expand the side with the division or the multiplication. Here we just have a power, so we bring the power over. And this is the calculus step right here. We implicitly differentiate, so the derivative of the natural log of y is 1 over y dy dx. We use the product rule on the right side, and the derivative of the natural log of sine x, notice this is the composition of two functions. We use that rule that the derivative of the natural log of u, where u is the inner function, is 1 over u du dx. So that's where we get 1 over sine x times cosine x. And similarly, we just bring the y over and then replace it. And I just rewrote cosine x over sine x as cotangent x, but you really don't have to do that. And here is our final answer, right here. Okay, let's move on. Let's try these two problems. Number 5 was a multiple choice from an old AP years ago. I can't see them ask this question again, but I'd like you to try it. And I also like you to do number 6 using logarithmic differentiation. So I will pause the video, give yourself some time to do it, and check your answer with me at the end. Okay, so let's take a look at our problems. In number 5, notice that we have a function of x to a function of x, where the base and the exponents have variables. So that's when we really need logarithmic differentiation. So we take the natural log of each side, like we have here. Okay, and so we have the natural log of each side. Then we use the rules of the natural logs to rewrite the right side, differentiate implicitly like we always do, and then bring the y over and substitute back. And when we simplify, the answer should be C. In number 6, we could use the quotient rule. It's not that bad with the product rule, but let's try it with logarithmic differentiation to get rid of the division and the multiplication. So first we have to get the point of tangency. We substitute 1 into our function and we get that the point of tangency is 1, 1. Okay, I set my function to y. I take the natural log and of course, and we use the rules of natural logs to expand the side that's complicated. And then we use implicit differentiation with the chain rule for the natural log to differentiate the natural log of a function. And at this point, I did not solve for dy dx. I just substituted x equals 1 and y equals 1 to get the derivative of the function at 1 for the slope of the tangent line. And when we work it all out, the derivative is 3/4, and it's so easy to compute this way. And we get that the equation of the tangent line is y minus 1, which is in green, y minus 1 equals 3/4 times x minus 1. So remember, if we know the point and we need the slope of the curve, we just differentiate and substitute. We don't have to solve for dy dx unless we have to, like in question 5. And now I'd like to get to the real use of logarithmic differentiation, and that's to prove the power rule for irrational exponents, like in number 8, x to the power of the square root of 2, or x to the power of pi. Okay, we'd like to show that the power rule works for these problems, even if the exponent is irrational. We proved the power rule for rational exponents using implicit differentiation. Now we're going to prove the power rule for irrational exponents using logarithmic differentiation. So this is what we do. We start writing this. But now let's say that the power rule was proven when n is a rational number. So now we're going to say, assume n is irrational. Okay, is an irrational number. So what we'll do is we'll take the natural log of each side. And even though n is irrational, and we have a natural log of x to an irrational number, we can move that irrational number in front of the natural log, right? And now we can differentiate both sides with respect to x, because now that irrational number was tricked into becoming a coefficient to a function. So when we differentiate both sides, we get 1 over y dy dx. The irrational coefficient is brought down, and the derivative of the natural log of x is just 1 over x. So now we isolate the y, the derivative, by bringing the y over. And now we bring the y back to what it was originally. And we use the rules of exponents now. So x to the n divided by x is just x to the n minus 1. And hence, we have proven the power rule for any kind of exponent. This proof would cover any exponent, whether the exponent is irrational, rational, an integer, any exponent. This would be the general proof, but I saved it for the case where n was irrational. So now in number 8, we are justified to say that the derivative here is the square root of 2 times x to the square root of 2 minus 1. And we would leave our answer just like that. The derivative of x to the pi would be pi x to the pi minus 1. Okay, it looks strange, but that's what the derivative would be. Okay, now in the next one, number 8, I'd like you to try 8 and 9 yourselves. Pause the video, try 8 and 9. Now be careful. I switched the roles of x in number 8, so be very careful when you differentiate that. Okay, so stop the video and try it. Okay, so in number 8, the derivative of x to the e always locate where the number is. The number is the exponent. The base is a variable. That's when we use the power rule, ex to the e minus 1. But the derivative of e to the x is an exponential function, and that is just e to the x. So the answer to number 8, the derivative would be e to the x to the e minus 1 plus e to the x. In number 9, we've got a variable as a base and the exponent as an irrational number. However, notice that the base is a function of x. So recall that when we differentiate a function of x to a power, we use the power rule where the outer function is the power and the inner function is the base. So the derivative in this case would be n, the base to the n minus 1, times the derivative of the inner function, which is the derivative of the base. So in this case, we get the square root of 3 times the x squared plus 1 to the square root of 3 minus 1. That's the power rule. Keeping the x squared plus 1 intact times 2x. And that's our answer for number 9. So that takes care of the lesson on logarithmic differentiation. Just remember that logarithmic differentiation is used when we have a function to a function and we want to get the derivative, or if y is an expression with division, multiplication, and powers. And a nice application for log differentiation is that we can prove the power rule for any exponent, including irrational exponents. And please note that the answer will always contain the original function, which is quite amazing that, and it makes sense, because if the derivative is derived from the function, then the function must be within it. And that's exactly what logarithmic differentiation does for us. And if you ever forget how to differentiate a function, if you forget the rule, you could always use log differentiation. Okay, that takes care of our lesson today. And I will see you soon in class. Take care now. Bye.